5 billion years from now, our sun will run out of fuel. Its core will collapse, its outer layers will eject into the vacuum, and the monument it leaves behind might look exactly like this. This is NGC 6543, known as the Cat's Eye Nebula. Captured here by the Hubble Space Telescope, it is one of the most intricate structural puzzles in astrophysics. In 1864, the first spectroscopic analysis of this nebula revealed the distinct emission signatures of gas. That discovery identified these shapes as the atmospheric remains of a dying star, distinguishing them from the distant star clusters they resemble. But the shape of that gas presents a strict physics problem. Gravity acts equally in all directions, which dictates that stars exist as perfect spheres. If a perfectly spherical star sheds its outer layers uniformly into space, the resulting gas cloud should expand outward as a neat, highly symmetrical bubble. Looking at this conceptual geometric model alongside the raw image, we see the exact opposite. There are overlapping ellipses, offset rings, and high-speed jets piercing through the boundaries. The expelled gas is wildly asymmetrical. This architecture functions as a cosmic fossil record. By mapping these gas structures, we can begin to reconstruct the physical forces that stripped the star of its outer layers. To understand the sequence of events, we have to look at this 3D wireframe schematic and examine the outermost boundary. Tracing the perimeter, we find a distinct bullseye pattern constructed from at least 11 concentric rings of gas. Calculating the expansion rate reveals these rings were not shed in a single explosion. They are episodic ejections. The dying star pulsed, throwing off a distinct shell of mass exactly every 1,500 years, like a slowing heartbeat. Moving inward to the core, the geometry shifts. The center contains two distinct intersecting elliptical bubbles, categorized by astronomers as E25 and E105. To explain these central bubbles, astrophysicists rely on a leading framework called the Interacting Stellar Winds model. In this model, a dying star releases a slow-moving cloud of gas, followed later by a burst of fast-moving wind. When the fast wind rear-ends the slow gas, it acts like a plow, compressing the material into sharp, high-pressure boundaries. That collision accounts for the smooth interior walls of those crossed ellipses. However, the fragmented structures erupting past the core remain unaccounted for in this model. These isolated narrow-band images expose the anomalies. Scattered along the perimeter are dense clusters of material known as caps, onsae, and jets. They exist outside the boundaries predicted by interacting winds. Spectroscopic data reveals these specific knots are chemically distinct from the surrounding gas. They are abnormally cold, highly deficient in hydrogen, and register a low state of ionization. Because they are so dense, these knots block the ultraviolet radiation pouring out from the central star. You can clearly see straight, radial ionization shadows trailing directly behind them, like boulders parting the current of a river. To explain how these dense, cold projectiles formed, researchers map out three distinct causal pathways. The first pathway examines magnetic fields. As the star's core collapsed, highly energized magnetic lines could have twisted and constricted the escaping gas, warping it into strange trajectories. The second pathway points to co-rotating interaction regions. Recent data indicates the central star is spinning fast enough to whip its outgoing winds into localized, overlapping spirals. The third pathway involves an unseen binary companion. A secondary star caught in a tight orbit would act like a massive gravitational egg beater, aggressively churning the expelled gas as it expands. Standard physics cannot recreate the cat's eye by isolating just one of these mechanisms. The mathematical models refuse to align perfectly with the shape. The climax of this investigation is a messy one. Astrophysicists now suspect the star is not using just one of these mechanisms, but all three simultaneously. Even after decades of observation, no single computational model is sophisticated enough to replicate the full chaotic architecture of the cat's eye. A star transitioning into a white dwarf is a violent sequence of events. A spinning magnetic core interacting with a companion star sheds turbulent plasma, creating an environment governed by competing physical forces. This makes the cat's eye an active crime scene, capturing the exact moments where stellar mechanics break down into pure turbulence. And 5 billion years from now, when our own solar system reaches its final days, our dying star will paint the dark with the exact same beautiful violence.